So this next video will be taking the product and quotient of complex numbers in trig form. So taking the product and quotient for complex numbers in rectangular form is pretty straightforward. We just use what we did for polynomials or using that complex conjugate, or just the conjugate, okay? Now for trig form, it's going to be a little bit different because now we're dealing with radius, theta, and then we also have our sine and cosine involved. So visually what this is going to look like is if we take the product of two complex numbers in trig form, we'll call this z sub 1, and then we'll call this z sub 2, okay? So z just represents a complex number. We have one complex number here and then a second one here. If I were to sketch our first one, let's make it here. We'll call that z sub 1. So z sub 1 has its own radius, and then it's also going to have its individual theta. We'll call that r sub 1 and theta sub 1. Our second complex number, we'll call it z sub 2. It will have a radius, we'll call it r sub 2, and then it also has an angle theta sub 2. Now, if we were to multiply these together, we end up multiplying the lengths of the radii together. All right, so it's going to extend a lot further than the first two we had. And then when we multiply them, we will add the thetas together. Okay, so I think based on the scaling, this would end up in quadrant 1 still, but pretty close to pi over 2. So multiplying those radii together, I end up with something like this. So this is r sub 1 times r sub 2. Then our angle, that is going to be theta sub 1 plus theta sub 2, all right? So multiplying complex numbers in trig form, this is what we will end up with. So we'll go ahead and try some examples down here. This one says multiply or divide each of the following. We're only going to multiply. Leave your answer in complex trig form where 0 is less than or equal to theta, which is less than 360 degrees. So our first complex number is 4 cosine 270 I sine 270. Forgot the notation there. And W is equal to 3 cosine 225 degrees plus I sine 225 degrees. All right, so this is our second complex number. This is our first one, and we want to find Z times W. So Z, I'm going to have a radius of 4. And then the radius for W is going to be 3, so we're going to multiply those together. And from here, we'll have cosine of 270 degrees plus 225 degrees. So remember, the angle for cosine and sine, it will always be the same. And what we're doing is we're adding the angle from the first complex number with the angle of the second complex number, because the sum of that angle will give us the angle for the product of these two complex numbers. So now we'll have plus I sine of 270 degrees plus 225 degrees. So now we have a new radius of 12. And when we add these two together, we'll have a new angle of 495 degrees. Now, the problem explicitly says that the angle needs to be between 0 and 360. And we notice that even in the complex plane, we can have coterminal positions depending on our theta. So we can go ahead and do 495 minus 360. And we'll end up with 35 degrees. Sorry, 135 degrees. So we'll end up with 12, and I'm going to go ahead and condense this. We'll have CIS 135 degrees. So in my examples, I will be condensing to the CIS form. I will only leave it expanded if we have to rewrite it in rectangular form or A plus BI form, because then we have to evaluate, and it gets a little difficult to see the evaluation in this form. So we're staying in trig form, so I'm going to condense it. Now let's try this problem. This says multiply each of the following. Leave your answer in complex trig form where 0 is less than or equal to theta, which is less than 2 pi. And we are doing Z times W. Okay. So We're staying in complex trig form, so I'm going to go ahead and start this as the condensed version, okay? So C times W will multiply the two radii, and now I have CIS, and we're going to add the thetas from each of the complex numbers. So we'll have pi over 2 plus 5 pi over 3. So the new radius is going to be 30, and we need to use common denominator. So common denominator will be 6. So we'll multiply pi over 2 with 3 over 3. So we get 3 pi over 6. And then multiply 5 pi over 3 with 2 over 2. So we get 10 pi over 6. So from here, 30 CIS, we end up with 13 pi over 6. However, this is out of our domain restriction because if we're going from 0 to 2 pi, with a common denominator of 6, that is the same as 0 to 12 pi over 6. So we need to subtract 2 pi from 13 pi, or in this case, 12 pi over 6. So 13 pi over 6 minus 12 pi over 6, we're left with pi over 6. So then we have 30 CIS pi over 6. All right, so that's how we find the product of two complex numbers in trig form. For the quotient, it's going to be similar as I'm going to use this drawing again. Actually, no, I'll do another one. Let's go ahead and do one here. All right, so we will have two complex numbers. Let's say that we have z sub 1. Z sub 1 will have its own radius, and it will have its own theta. And then let's say z sub 2 is over here, a little bit smaller, quadrant 2. So this is z sub 2, has its own radius, and then it'll also have its own angle. We'll call it theta sub 2. Now, what if I did z sub 1 divided by z sub 2? What's going to happen is the radius of z sub 1 will be divided by the radius of z sub 2, so we're left with a bit of a smaller radius. And then the thetas, we are going to find the difference in those thetas, all right? So the new theta will be theta 1 minus theta 2. Because theta 2 is larger, that's going to push me into quadrant 4. So I'm doing theta 1, and I'm going to go ahead and subtract theta 2. So this is theta 1 minus theta 2. And then the radius, it's not going to be really to scale. We can say that it's here. Okay, and this will be R1 divided by R2. Now, theta 1 minus theta 2, we'll end up using this angle because we have to be from 0 to 360 or 0 to 2 pi. Okay, so this will be equivalent to theta 1 minus theta 2. All right, so visually it gets a little wild, but algebraically I think it's easier to see what's going to happen. All right, so this was part A. Now we're looking at part B. So we're dealing with the same two complex numbers we had before, but now we're doing W over Z. So complex number W is 3, it'll be cosine 225 degrees plus I sine of 225 degrees. And it's divided by complex number z, which is 4 times cosine of 270 degrees plus I sine of 270 degrees. Now, if you look at this, you can see the ratio of the radii. So the new radius is 3/4. And then we will have cosine. We'll do top minus bottom. So we'll have 225 degrees minus 270 degrees plus I sine 225 degrees minus 270 degrees. And now I'm going to go ahead and condense this because we're not converting to rectangular. So we'll have 3/4 CIS, 225 degrees minus 270 degrees. We end up with negative 45 degrees. So this is similar to what happened in the example I showed, we have two complex numbers. One is 225, so that's in quadrant 3. The other one is 270, that's right between quadrant 3 and 4. But when we take that bigger theta and subtract it from the smaller one, this puts us all the way back into quadrant 4, but with a negative coterminal angle. So now, in order to stick with our domain restriction, we have to do negative 45 degrees plus 360 degrees. We want that coterminal angle so that we are within our domain restriction. And that's going to give us 315 degrees. So the product is going to be 3/4 CIS, 315 degrees. Now for this other example, part B, we are finding the quotient W over Z. And because we're not converting to rectangular, I'm going to stick to the condensed version. So W is 6 CIS, 5 pi over 3. And then Z is going to be 5 CIS, pi over 2. All right, in this format, we can already see the ratio of the two radii. So we'll have 6/5, and then CIS, top minus bottom, we have 5 pi over 3 minus pi over 2. And we need that common denominator again, so we'll do 6 again. So we end up with 10 pi over 6 minus 3 pi over 6. So we end up with 6/5 CIS, 7 pi over 6. All right, in the next video, I will talk about de Moivre's theorem. Hope this helps.